Here I've got a two-phase system of ice and water in a beaker at 0 degrees Celsius. And what I've got above it is the reaction vessel, which we are going to use to measure the enthalpy of the reaction. Now, right here, I've got a burette, which is full of water, and I've got its counterpart over here so that I can actually get water above the water line at a level which can be measured in a burette. You can see right here that the water level is about here, which means it should be over here. But because ice melts and that this is closed, that means the water level is going to decline on this side, and eventually at some point it'll get down below any sort of reading mark we can get. So if we open up this stopper and then we close it up, what we can see is the water level raises, and then it starts to slowly move back down again as ice continues to melt. And the reason that this is occurring is because the ice is melting, and ice takes up more space than liquid. And so as the ice melts, the water level moves down. And what is going to happen is this is going to continue to occur during the course of the experiment. But what we want to do is try and minimize that. And we're going to minimize that by placing this into a bucket full of ice and then insulating it as best we can by packing it down with ice. Now, before I do that, back here, I've got a little test tube, and you can see that the test tube is mostly submerged down here. So I've had some acid sitting in this beaker for a while, cooling off, because we want the reaction to occur at 0 degrees Celsius so that it's within thermal equilibrium of the environment. And so any ice that melts will be solely from the reaction and not from the cooling effect of the ice chilling off the acid. Now, like I said, the outside environment is going to continue to put heat into the system, so the ice is always going to be melting. So what we're going to do at this point is really try and slow that down by packing this beaker and surrounding it with ice and then putting some on top as well to minimize that thermal input. And that's really going to slow down the rate at which this water level is moving. It won't eliminate it, but it will bring it down to a very, very slow rate. The reason we need to check the background melting of ice is because while it is occurring, we should see a change during the course of the actual reaction occurring. That is, this will start to drop fairly dramatically and very quickly. And we don't know when the reaction is going to be done, so we have to have an idea of what the rate of melting is prior to the reaction, so we can compare it to the rate of change of this ice movement or ice melting when the experiment's done. That is, we're going to measure the time for this experiment quite extensively so that we are absolutely 100% certain that all the heat of the reaction has been measured and we're basically back to background ice melting. So I'm going to go ahead and throw this into a bucket of ice and top it off, and then we'll end the video. So what you can see here is we've got the instrument now thermally insulated as best we can. So we've covered the whole thing with ice, so that's going to minimize the energy input from the room and really just allow the reactions heat, which I'll turn this here, the reactions energy, which is occurring in here, to be the only energy input into the beaker causing the ice to melt. So hopefully this has helped clarify some of the procedural setup and what's going on, and we'll see you with the next lab.